Everyone, thanks for joining me today. My name is Jerry Peng, and I'm here to talk about how we at Splunk built a real-time stream processing platform with Apache Pulsar and Flink. And Caroline, you can see my slides, correct? And you can hear me as well?
Yes, we can. Thank you.
Okay, thank you. So on the agenda for today, I'm going to first give an introduction about Splunk in case people aren't familiar with our company. Then I will give an introduction of SPS, the stream processor service that we have built at Splunk to do stream processing. I will subsequently go over the architecture of SPS, essentially how basically Pulsar and Flink is used. I will also talk about how a user interacts with SPS. And lastly, I will talk about some of the observability pieces we have implemented in SPS. So first, let me kind of introduce our company Splunk. Traditionally, you probably know Splunk as the platform in which you dump all of your server logs into, and Splunk is the platform that enables you to search and analyze those logs. However, Splunk has evolved into much more than just a simple machine log query use case. Today, we really like to categorize Splunk. We at Splunk really like to categorize what we're doing or building as a data to everything platform designed to unlock trap value by bringing data to basically every question, decision, and action to the user. It is really designed to kind of remove the barriers between data and action so that people and businesses can turn data into doing in real time, and actually also know that what the actions that they have performed is backed by tangible data. So no longer can Splunk only just do perform the ingesting and log querying use case for server logs. Nowadays, people can send a whole variety of data from various sources and produce basically actionable insights on that data. So to become kind of the best data to everything platform, Splunk has definitely realized the importance of stream processing. As you imagine with all the icons in this screen, like data arrives in a variety of sources and data arrives continuously in a stream. So next slide here. Like I said before, at Splunk, we definitely realize the potential and need for stream processing, especially due to the rise of several popular use cases that I have depicted here. To start listing them, real-time monitoring and notifications, interactive applications from smartphones and smart devices, the classical log processing and analytics, IoT analytics, streaming data transformations, real-time analytics, data distribution, and event-driven workflows. People have definitely started to realize the benefits and opportunities that can be exploited by acting on their data faster. And we at Splunk really want to give our users, both internally and externally, the capability of doing that. So let me just talk about kind of what is common among all of these use cases. Data arrives continuously in a stream. Data is from these various sources is time sensitive. Data needs to be processed and delivered to its destination in a timely fashion. If it doesn't, if you don't do that in some sort of time window, you might lose certain opportunities. So all of these kind of use cases require basically a good reliable platform to basically process these streams of data. So that is why at Splunk, we have built the Stream Processor Service, or SPS. It's previously known as DSP, the Data Stream Processor. So we have really built this platform to enable users to implement the real-time processing use cases that I previously talked about. Users can basically send both unstructured or unstructured data from multiple sources and quickly turn large volumes of raw data into rich and contextual insights. as in this picture is depicting, users like are able to basically ingest from a wide variety of data of different formats and of different sources into SPS, and they're able to leverage a rich suite of functions to basically apply and transform that data, and then eventually send them out and route them to basically the desired or appropriate destinations. Let me continue here. So in order to kind of build a stream processing platform that enables users to basically, to implement the kind of workflows or applications that I talked about previously, we've come up with kind of a list of requirements for the stream processing system, and I think it's worthwhile to kind of discuss those before going into how we actually designed for all of them, and why kind of some of the reasons why we definitely chose to use Apache Pulsar and Apache Flink. So number one is scalability. We definitely want our stream processing platform to be scalable, that it can handle basically a large volume of data, and as the volume of data increases, we can scale to scale to even larger volumes. The second is durability, that once data enters kind of the stream processing, this processor service, that it is durable, that we're not going to lose the data in any kind of in any situation, so that the user basically can trust their data with us. The next thing is fault tolerance, that we understand that environments that we operate in, especially in the cloud or on-prem, might have errors at either the hardware level or the even underlying infrastructure level. So we want our platform to be able to handle those kind of failure scenarios and still be able to operate within kind of the designed parameters. High availability, this kind of touches in on the fault tolerance as well. So in the cases where there are faults and there are network partitions and so on and so forth, we want to be able, first, for our platform to be able to support deployment models that allow us to have high availability. This means we can deploy in different availability zones or regions, and in case there are failures in a sort of regions or availability zones, that we will still kind of be available. Sharing and isolation. This is primarily most important kind of for on-prem or even SaaS kind of offering of SPS, that in a multi-tenant scenario, in a situation, we want to be able to operate a multi-tenant service in which resources can be shared across our tenants, but also for the cost of scale kind of reasons, but also have a sense of isolation, so that you don't have these scenarios where there's a kind of a noisy neighbor problem in which what one tenant is doing might affect what another tenant is doing. Operability. So we have a couple of environments that we operate SPS in. We want to be able to basically, leverage, we want to be able to be optimized for operating in those environments, which primarily would be in the cloud, and also for some use cases on-prem. So we want to be able to operate the platform successfully in those environments. Observability is very important as well. We want to basically observe how basically our platform is doing, how certain aspects of the platform is behaving, and most importantly, if there is an issue, like we want to be able to debug those issues in a very timely manner, and that's how this observability, why observability is so kind of important for this platform as well. Disaster recovery. Kind of touched up on this in terms of fault tolerance and high availability, is in case there are disasters, how fast, and we should be able to recover in a speedy fashion, and there should be avenues in which we can recover. Cloud native. One of the big pushes for Splunk is to the cloud. So our platform definitely needs to be able to operate in kind of a cloud native fashion. And this also kind of touches on scalability and so on and so forth, that in operating in a cloud environment, we should be able to leverage all the resources, available to us in the cloud and, scale in the cloud as well. Because, Splunk does have, a large number of customers on-prem, that we should still be able to support some on-prem use cases in case the customer has that demand to be able to deploy, SPS in an on-prem environment to kind of satisfy, some of, our on-prem customers' streaming needs. So because of, the list of requirements I listed kind of before, we decided to use kind of the following technologies. One is Kubernetes. SPS runs both in the cloud as well as on-prem on Kubernetes. It serves as the platform, scheduler, orchestrator of all of the different components of SPS. The next major component is Pulsar. Pulsar was was designed with many of the requirements I listed in mind. So it really definitely is a good choice to be used in SPS, especially for kind of the, as the data nervous system of the platform to basically route data and move data to various aspects of the platform. And Flink is also used because it satisfies all the requirements that I've listed before to do some of the very complex data processing and analytics required by some of the use cases that we would like to basically enable our customers to do. So because this is a Pulsar summit, this is a Pulsar meetup, I would like to kind of talk a little bit more about kind of the history of Pulsar at Splunk. So Splunk, began to explore Apache Pulsar, a couple years ago into, how, they can leverage Apache Pulsar within existing, SBS as well as other systems at Splunk. So what really, kind of pushed Apache, Pulsar, what Splunk really began to explore Apache Pulsar more seriously is when, Splunk acquired Streamlio, which I was actually, a part of. And at Streamlio, we worked a lot on Apache Pulsar and developed a lot of that expertise on basically Apache Pulsar. So after acquisition, there was basically essentially a bake-off between Apache Pulsar and various other, technologies. And my manager and coworker, Karthik Ramasamy, actually gives a pretty good presentation on the results of that bake-off and a lot of details of the benchmarks we have done. But essentially, the gist of it is Apache Pulsar was picked as the de facto, mass messaging and queuing platform at Splunk. So what happened is Apache Pulsar, replaced the various like messaging and queuing platforms that were at that time used at Splunk, which would be Apache Kafka for the SPS on-prem deployment and AWS Kinesis and SQS in the cloud deployment. So it was a big win, I think, for Splunk, because it really kind of consolidated the various messaging and queuing platforms into one. So we'll no longer we have to kind of have different deployment scripts and deployment settings for on-prem, and in the cloud we can just use Pulsar for all of them. And Pulsar is really designed for both designed to operate very well in both kind of an on-prem setting as well as in a cloud deployment as well. Next, I kind of want to talk about and a little bit more is Pulsar IO at Splunk. We're not only kind of using the the core Pulsar functionality, the broker, the pub sub use case and the queuing use case, primarily broker, bookies, and ZK. We also use leverage other components of Pulsar as well, primarily Pulsar IO. So so at Splunk we have built a connector platform called the Unified Connector Framework, UCF, to basically power all of the connectors, sources, and sinks for SPS. So UCF would be responsible for all the data ingestion and also data egress of SPS. So this is a platform basically that allows users to run any sort of any type of connectors to basically ingress and egress data, from the platform. And UCF was built to kind of replace some legacy existing platforms that were used at Splunk, and we really wanted to basically, leverage first of all open source and also some of the advantages of the Pulsar IO platform, especially given that we're using Pulsar as the message bus and the data nervous system and within SPS. So I also gave a talk on some of the reasons give a talk and provide more of the details and reasons why we decided to come up with this new platform UCF based on Pulsar IO to replace the existing LSDC platform at Splunk. And I give some more details on what were the decisions made and how we evaluated the Pulsar IO platform. So I would encourage you everyone to kind of listen to that talk as well that I gave in last year's Pulsar Summit. But the general idea is depicted in kind of this diagram here, where we have a wide variety of basically sources or external platforms that we basically could ingest data from, and we're leveraging the UCF platform to basically get the data from those external platforms and ingest it into SPS or DSP, and also basically a set of connectors or sinks to be able to egress that data into Splunk Enterprise or a variety of other systems. So one of the things that we also contributed, we created at Splunk and contributed to open source is kind of the Pulsar IO batch source. Because at Splunk there are kind of two different types of ingestions that we work with. The classic stream, the streaming data ingestion, which Pulsar IO kind of is already designed for. But there's also more workflows that are more batch oriented, like collecting data from S3 that you want to kind of periodically go and fetch the data and ingest it. So at Splunk, we also created the batch source for Pulsar IO that allows you to basically perform these kind of more batch-oriented workloads. And UCF is really designed as a platform that allows users to run connectors that are more oriented towards the streaming nature as well as batch nature as well. So it's really a unified platform, and or you can think about it as a connectors as a service to allow users to run a wide variety of connectors that have different types of characteristics. So let me now dive into kind of the architecture of SPS, and this is kind of where all the interesting information is how we're actually in SPS we're using Pulsar and Flink, and this diagram kind of illustrates the high-level view of how the major pieces at play here. So in general, the data, you can see kind of the data flow in SPS is, data arrives to my left here. Data arrives from various ingest services and connectors. They all will flow into Pulsar topics. The data will be routed through various Pulsar topics to basically different Flink pipelines, which will then do some sort of processing, transformation, so on and so forth, and send the data to basically either Splunk indexers or some external system. So let me kind of decompose or discuss this more in detail. So on my left here, there's really there on the top left here, there are a couple of ways to ingest data into SPS. One is using kind of an HTTP model. We have a REST API service in which users could send data through kind of an HTTP protocol in the HEC format, which is a proprietary Splunk data format through HTTP, and it can be ingested into Pulsar and then be processed downstream. The other way to kind of ingest data into Pulsar is through the forwarders. People probably familiar with Splunk knows that this is kind of traditionally how data is sent to Splunk in general, is by configuring forwarders and your various, systems, and the forwarders will basically forward the data in this S2S protocol format into Splunk indexers. So for SBS, it's also able to basically ingest data in this format, send it to Pulsar, and then also route it to the appropriate pipelines for processing and send it downstream. So those are the two kind of the ingest services that we offer to support the existing protocols people have used to ingest data into Splunk. But now basically we're not going directly to Splunk indexers. We're going into SBS, which enables users to do some processing on that data and those formats as well. So the next kind of category of data ingestion is through connectors that we built using the unified connector framework based on Pulsar IO. So we have a suite of connectors. I will talk a little bit more about them in a later slide that basically can ingest data, for example, from S3 or Kinesis into Pulsar. Pulsar will then route them, to appropriate Flink pipelines for processing, then send them out. So those are, another way for users to connect data from, external systems and bring that data into SVS. A big part of kind of, how the glue that kind of holds all of this, together is we have built a control plane and, kind of a REST API service that basically allows users to interact with and to, perform a lot of the, the tasks within the service. So this control plane, users will typically, interact with the control plane directly and not really interact with, internal services as Pulsar and Flink is to SPS. So this is also serves as a gateway for users to leverage the functionality and capabilities of Pulsar and Flink. So what the users can do, how the users can interact with the control plane is, for example, start connectors to basically ingest data into their topics, and then also provision pipelines in Flink to basically process the data they're ingesting, and then write them out and have other connectors to basically egress that data out to external systems. So the typical workflow of kind of like user onboarding would be something like this. When a user basically is onboarded to SPS, topics, through the control plane will be provisioned. Ingest topics will be automatically provisioned for that tenant, and then basically the user can then go to a UI which interacts directly with the control plane to basically submit connectors, or start ingesting from ingesting data from the REST API, or through the S2S format into Pulsar. And then the user could also provision pipelines, kind of read from the various topics that they choose that they want to basically do some sort of processing. So let me kind of go into a little bit more detail of exactly how things work. So just to kind of first go over some of the terminology we use in SPS or DSP is in SPS we have the idea, the concept of a stream. But what a stream is essentially kind of a Pulsar topic, but we have some metadata on top of the Pulsar topic, such as quotas, rate limiting, and so on and so forth. So we call kind of the abstraction we use here is called a stream, but like I said, essentially it's just powered by a Pulsar topic. And we have the terminology called a pipeline, which essentially is just a Flink job. So like I mentioned before, there are kind of three different workflows that that I would like to illustrate for SPS. One, like I mentioned before, is you ingest data through forwarders and the HEC format, and they go to the various ingest services that can then write the data into various streams. There's a default stream that we call the fire hose, that if the user doesn't specify kind of which stream or topic to go to, like the data kind of just goes there. So once the data is in a stream or Pulsar topic, the user can then orchestrate these pipelines. That basically the point of the pipelines is to manipulate stream from one state to another, right? It's kind of, you can view a pipeline as a function in which the input, is a stream and the output is a stream as well. And we eventually will then leverage, our UCF connector framework to run basically sinks to egress that data into, desired external systems or, to Splunk indexers. The next kind of workflow is, through kind of running UCF source connectors to ingest data from external platforms like S3 and Kinesis, write them into, basically move that data into an internal stream or Pulsar topic, have pipelines manipulate that, and eventually write them out to the appropriate destinations as well. We also kind of have an interesting idea with kind of external streams in case, you're connecting to an external message bus and you don't really want to kind of, move the data into Splunk, right? For whatever reasons, we kind of have the idea of supporting the idea of external streams, like reading directly from Kinesis into a pipeline and then writing them out as well. So in the previous slides, I kind of went over, gave an overview of some of the core services, more from the perspective of, kind of explaining, how Flink and Pulsar really is used in SPS. But in reality, because SPS is kind of a multi-tenant service with, quite a bit of, functionality in terms of user management and, and whatnot, it actually has kind of several components here as depicted kind of in this diagram. Like there's several components, like where you're leveraging Vault and Postgres for, authentication, for, user management, and for also data management. Here, and this is really a diagram that depicts how kind of we run on-prem. So we're also leveraging object stores like Minio for on-prem, but in the cloud, where we would be leveraging, existing, cloud object stores such as S3 and, and GCS and whatnot. So there's definitely, a lot of other components other than Apache Pulsar and Apache Flink that allows basically, SPS to run in the manner, it does as a multi-tenant, fully featured service. So now let me kind of go over how we, so I've talked about kind of, the overall architecture of how Apache Pulsar and Flink is used in SPS. So kind of to connect the dots of how actually users would interact with the SPS platform, right? I would like to, talk about how users kind of, build, workflows or pipelines, data workflows or pipelines to leverage the capabilities of SPS. So one way is to, go to the UI and, we have a simple kind of a drag and drop UI in which a user can orchestrate basically, a data flow or a pipeline from there, and they could leverage basically existing sources and functions and sinks that we have built to basically, to orchestrate a pipeline. And the key here to note here is that we have a rich set of sources, functions, and sinks for users to pick from. So the users are not actually writing actual code. They're basically picking from a rich suite of existing functions to orchestrate their pipelines. Another feature, pretty cool feature we have is, instead of if you're more of an advanced user or you're more familiar with kind of the Splunk ecosystem or with using kind of Splunk Enterprise, you can orchestrate pipelines directly by writing SPL, which is a SQL-like language for that Splunk uses to query data. And this was first used kind of in Splunk Enterprise or Splunk D to query data within indexers, but we've also brought that functionality to allow users to orchestrate pipelines as well. So you can just write, at the SPL, and then it will basically be translated or parsed into, a pipeline as well. So, kind of how that works is, if you're familiar with translating, SQL or any sort of query language into, a stream processing job is, a similar idea. You have the SPL, you have a parser and query planner, and then eventually it gets, converted into a Flink job of sources, operators, and sinks. So, we have that as well to allow users to use the existing kind of, SPL and, Splunk language to basically orchestrate pipelines from that perspective. And it's kind of a general um, it's kind of a one of our future goals is to is to unify kind of stream processing and batch processing, both leveraging functionalities and SBS as well as indexers to really unify data processing and build a platform to unify data processing for the end user. So like I talked about before, like, a big part of SBS, and I think a big part, what I think is also a big part of the success for SBS is how SBS is able to kind of integrate with, external systems, right? At the end of the day, like, users need to basically bring data from somewhere else into Splunk to get them processed and eventually maybe send them out somewhere else as well. So, in SBS, we've worked, very hard on also, building a wide variety of connectors that allows users to safely and reliably, egress data to, popular to and from popular external systems. Of course, we have the, Apache Pulsar sources and sync in case, you want to basically bring data in from an external Pulsar data or write data out to external Pulsar cluster. But there's some other, popular sources and syncs that we have built: CloudWatch Metrics, S3, Kinesis, Event Hub, Kafka, and and many more. Like I mentioned before, users could also just ingest data via an HD protocol, the HEC protocol, or S2S via the Splunk forwarders if they like as well. So we definitely offer like one of our big initiatives is to make it very easy for users to basically bring their data into SBS and Splunk as well. So another core piece of SBS is the functions, the functions that we already built, right? So you can think of a pipeline as sources, the functions in between, or operators, and then sinks, right? So in SBS we have also invested a lot of time building functions to allow users to kind of orchestrate their pipeline, so that at the end of the day, we don't want users to kind of write any code. We want users to basically just leverage already pre-built functions to basically to satisfy their use cases. So we have, we definitely have a lot of simple functions like filter, line breaking, and all the, the gamut of, simple functions that you can imagine to do simple things. But what is also cool is, SBS also offers a suite of, online machine learning functions, and we have a whole, machine learning team dedicated to basically this kind of research, to basically bring machine learning to stream processing as well, which is honestly kind of a new frontier. So some of the things we offer is like time series decomposition, outlier detection, sentiment analysis, and there's a whole, a range of machine learning functions are available to our users, on our website as well. And this is, these functions you can view as what really kind of brings the value to our customers, leveraging basically a lot of the work we have done, reusing kind of the work we have done across many users, and this really basically instead of the users implementing kind of these functions, it allows the user to really kind of focus on business logic instead of the details of stream processing. The next thing I would like to touch up on is deployment, of how basically we're deploying SBS and how we're deploying Apache Pulsar and Flink. So SBS has two deployment modes, as I kind of touched upon before. One is in the cloud, and it's kind of a SaaS multi-tenant service. And also we have another deployment mode we support is on-prem, which is primarily single tenant for our on-prem customers that require this functionality. So like I said, SBS runs on K8s for both cloud as well as on-prem. So we're not really we're leveraging Kubernetes for both our on-prem and cloud deployment, so that we don't really necessarily have to have two separate deployment scripts of how we deploy individual services. We can assume that there is Kubernetes, and then we can basically deploy on Kubernetes. But how we're deploying on Kubernetes is a little different in the cloud than on-prem. In the cloud, we have a Kubernetes team that basically deploys our own Kubernetes version on VMs. And for on-prem, we're kind of leveraging this tool called Gravity to deploy Kubernetes onto basically raw machines, and then we can spin up SBS on top of that as well. And we're also looking into deploying basically kind of in a slightly different manner, and probably even I would say a very interesting manner, is instead of deploying on our own Kubernetes deployments, whether it's deployed on-prem or the cloud, we want to kind of leverage also existing cloud provided hosted K8s environments like GKE and EKS to basically deploy all of that in. And there's definitely many advantages to leveraging the existing hosted K8s environments in the cloud as well. So let me talk about kind of some more details of how some of the key, interesting maybe configurations that we're using for deploying, Pulsar in the cloud as well as on-prem. So in the cloud, we're leveraging, EBS in AWS for, bookie storage. Because EBS is, replicated and, fault tolerant, we've decided that it's good enough for our ensemble size, Y quorum and A quorum to just be 2, which means there are 2 kind of replicas for the data written to Pulsar. And we're also leveraging kind of namespace level policies such as producer rate, dispatch rate, and other quoting capabilities in Pulsar for multi-tenancies, as I explained, like SPS. And the cloud is a multi-tenant service. For on-prem, we're primarily using local SSDs for bookie storage. So because of this, because of this, we're kind of setting the ensemble size, right quorum and A quorum to be 3, which means we're kind of writing 3 replicas of the data onto storage. So there's, obviously this is all configurable, but some of the reasons we decided to kind of increase the number of replicas on-prem is to basically have more reliability for more durability for our data, because on-prem, especially if a user is deploying technically on-prem, but they're also deploying in the cloud, local SSDs are kind of ephemeral. So if a VM restarts, you're kind of losing that data. So we decided okay, it's better to have a higher kind of replica count. And a lot of the on-prem use cases, they kind of want to kind of get the most out of their infrastructure. So a lot of them leverage local SSDs for better performance, but the downside for that is if you're in the cloud, they're kind of ephemeral. So we've for some deployments, we've basically increased the number of replica count for deployments on-prem. So for both in the cloud and on-prem, we deploy basically to be fault tolerant and tolerate availability failures. So which means we have bookie rack aware is enabled. So we spread basically our bookies into correct zones, so that if there's a zone failure in one, we're not going to lose all of the data. We basically can recover from that situation. And Zookeeper is also pinned across different availability zones as well to prevent the same thing. So I talked about deploying kind of Pulsar, but let me also talk about kind of deploying Flink. Initially, in SBS, we've deployed Flink as session clusters, which is like one large cluster to run all the pipelines. So some of the benefits of that is that we reduce resources cost per pipeline, because everyone kind of run as threads within task managers and Flink. But the obvious problem there is the noisy neighbor problem. Everybody is sharing this one large cluster, and if one tenant or user is basically hogging all the resources or having a large pipeline, it might affect the performance of pipelines of other users. So we've moved basically our deployment model for Flink into using job clusters. So basically each individual pipeline is a cluster itself. So this basically allows us to have better, pipeline isolation and better basically resource guarantees for each individual pipeline, and allows basically us to be better at basically reproducing the performance of a pipeline, giving a set of configurations. So we definitely moved to basically deploying pipelines using job clusters in SPS. Also, what we have spent time implementing or is still implementing is, fully function control plane for Flink jobs that really manage kind of the life cycles of Flink jobs and Flink jobs within SPS. And one of the cool things we're doing is, within the control plane is auto tuning of the pipelines to basically in the future dynamically scale, right? Dynamically scale and tune basically the parallelism of the pipelines without human intervention. So observability, like I kind of mentioned before, is very important for us as well, because we want to operate a very reliable and fault tolerant service. So we definitely need basically visibility into kind of the platforms we are running to make sure they're healthy, and in case there is an issue, be able to debug that issue very quickly. So we've invested a lot in kind of the observability of the pipeline. Some of the tools and that we use for observability is Splunk, which is Splunk indexers. Obviously, we kind of dog food our own platform at Splunk. So all of the logs from Pulsar, Flink, they're all sent to Splunk indexers that developers can query to see what is basically going on in terms of logs for those platforms. Another tool we use is Prometheus. We're running on Kubernetes, so it's obvious. It's convenient for us to use Prometheus to basically scrape metrics from all of our containers and pods. And then we also leverage Grafana to do some dashboarding of those statistics that are sent to Prometheus. Deployment. So we have observability for deployment. We have basically dashboards created and in the Splunk interface to tell us what version of Pulsar is running, how many tenants there are, and so on and so forth, and metrics on what is what are the top errors and latest errors. So we built a number of dashboards in Splunk itself to give us the visibility into actually our deployment of Pulsar and Flink to make sure that we know what exactly is deployed in our different environments. The next key thing we have in our observability is, we've defined certain SLOs with, our customers, and we want to be able to maintain those SLOs. So we have a, list of dashboards to monitor, the individual SLIs to make sure that, we are meeting those SLOs. And if we're not, someone should be, notified to see if there's any sort of potential issues. So we're leveraging, we have a set of dashboards to maintain that, we are at the level of performance that we have, told, our customers. The next big thing in observability is logs, like I mentioned before. Like all the logs are sent to Splunk, and we can leverage, all the functionality of SPL and Splunk to query the logs. So this is, where, we can definitely, leverage the existing kind of, log search capabilities of Splunk, and it really helps us, determine especially some of the high level statistics, like how many times did a particular error occur, what are the different types of errors, right? Like what are the different, if there are errors, where are they mostly coming from? All of these questions you can be easily answered by or by creating these queries for the logs out of coming from basically our platform Pulsar and Flink. So I also talked about that we use Grafana at Splunk as well to basically monitor, both Pulsar and Flink. And for Pulsar, we're definitely leveraging the open source dashboards that I've listed here on GitHub. That we're leveraging the suite of dashboards to basically get fine-grained statistics on on topic metrics, broker metrics, ZK, and bookkeeper, all of those as well. That's available, for everyone. We're running those dashboards as well internally. And for Flink, we have set of dashboards to monitor jobs, performance, backlog and Pulsar are one of the important things to make sure like we don't have a backlog. Also checkpoint size. So all of these fine-grained metrics to really help us if there's an issue in these specific systems to be able to help us debug what the issue is. We also, in general, we have basically Grafana dashboards to basically gain insights in just the general container and JVM information about Pulsar and Flink. Both of the projects are written in Java, so it's really important to kind of monitor the heap usage, directly memory usage, and the GC pauses and so on and so forth to see if there's a problem. Could the problem arise in those areas as well, not having enough resources, so on and so forth. So, and lastly here, I want to kind of touch up on some ongoing and future work that we're doing. So one of the cool things I think we want to do is, we want to add, tracing through Pulsar to improve monitoring and debugability. So any sort of basically event that happens, like create topics, create ledger, like we can basically, trace through the platform to be able to understand when did certain things happen, and if there is a problem, have basically a timeline of when certain things happen to allow us to have insights into what possibly could have gone wrong. And since we're leveraging the Pulsar IO and functions platform extensively at Splunk, we're continuing to improve and optimize those platforms for running as well. Auto partitioning, this is something that we will like to be working on in the future so that users don't necessarily need to specify a number of partitions. We can just basically, specify some sort of target or SLO, and Pulsar will automatically kind of adjust the number of partition count for you. This is an ongoing project, as well as the pluggable metadata store, is to abstract kind of Zookeeper, to abstract where the metadata for Pulsar is stored in a way so that we're not so coupled with Zookeeper, and we can potentially leverage other systems for storing metadata. Enhancing state store. So state store is primarily used kind of by the Pulsar IO platform to maintain state. So state store is a project that is part of Apache Bookkeeper. We're really kind of building a key value store on top of Bookkeeper, and we're basically enhancing and hardening the state store because we leverage it so much in Apache IO. So there's definitely a lot of work in terms of, especially in terms of hardening and getting state store into into a better and more production ready state. Another ongoing kind of project we're working on is distributed rate limiting. There's a PIP for that, and this is an ongoing project to basically provide rate limiting across many topics. Currently, the rate limiting is basically enforced at a per topic granularity, but in the future, especially for fully featured multi-tenant service, we would like to do rate limiting and enforcement across multiple at the multiple topics level, on the namespace level, to allow basically set basically a rate limit at a Pulsar namespace level to say, okay, all the topics within basically this namespace, the maximum basically data rate that they can achieve is at this high watermark. Yep, that's all I have to present today. Thank you for joining me today. I guess, Caroline, should we go into
Yeah, absolutely. Sorry, let me just, we have about 10 minutes for Q&A. And while we're waiting for some questions to pop up, I just wanted to take a couple of minutes and do a brief intro of Stream Native and also mention some upcoming Pulsar events. So actually, if you can stop sharing for a second, I will go ahead and do that. Okay, great. So first of all, thank you again. Such a great presentation. And for everyone on the call, if you guys want to go ahead and start putting some of your comments into the questions, we'll go ahead and jump into those. So just to share, I know we have a lot of Flink people on the call and maybe even some Pulsar people that don't know Stream Native. So just to introduce the company, Stream Native is really the company behind Apache Pulsar. We were founded by the original developers of Apache Pulsar and really have been supporting and promoting the community over the last several years. So we have our CEO, CJ Guo. He was one of the original developers of Apache. Today, he's a Pulsar and Bookkeeper PMC member. We have our CTO, Matteo Merli, who is the Pulsar PMC chair. And we also have Zhao Zai, who is another Pulsar and Bookkeeper PMC member. Last year, we launched Stream Native Cloud, which is a fully managed real-time messaging and streaming platform powered by Apache Pulsar and now Flink. So very relevant to our topic today. We have been working really closely with Ververica over the last several months. Stream Native and Ververica are now cloud partners. And a big reason behind that is because there's such a synergy between both Apache Pulsar and Apache Flink. And as part of that, we're super excited. This is an announcement we made last week. We just announced Flink SQL on Stream Native Cloud. So we'll share a link if you want to read more about this. I won't take too much time, but you should see that in the chat. And then really the goal behind this is that with Pulsar and Flink, as we've heard about on this call, companies are really able to leverage the power of stream storage and stream compute for a complete streaming solution. So just want to quickly intro that, let you guys go ahead. If you want to find out more, you can ping us directly or visit us at streamnative.io. If you want to learn more about Apache Pulsar, there are a number of upcoming events. We actually have a crash course on Monday. There will be a link in the chat for that. We also offer an intro to Apache Pulsar 101. There was one actually this morning. We'll have another one May 26th. It's free to join. Share it with your colleagues. We'd love to have you on that call. It's hosted by Addison Hyam, who is Stream Native's chief architect. He has worked on Apache Pulsar in production across many different deployments for a number of years. So great for any Q&A that you have. And also want to mention the Pulsar Virtual Summit North America 2021. This is being hosted by Stream Native and Splunk. We will put a link in the chat so you guys can go ahead and sign up for that. We will be updating the Pulsar Summit website this week with the finalized schedule. So lots of exciting news. And with that, I will pause here and we can jump into the Q&A. Let's see. I don't see any questions in. If you guys want to drop the questions directly into the Q&A, it's a bit easier to manage. I know there were a couple of questions in the chat. One is UCF based on Pulsar IO an open source project? If so, can you please send me the link to the GitHub project?
Yes. So yes, UCF is based on Pulsar IO, and Pulsar IO is open source, and it's just part of the Apache Pulsar repo.
Awesome.
There's already an existing set of open source connectors there that are supported as part of Pulsar IO.
Great. And then a question from Reese. Did you consider using Pulsar stream processing instead of Flink? I think they mean Pulsar functions.
Yes. So Pulsar functions and Flink, they kind of occupy, they kind of are used for, two separate types of use cases. Flink is more for, complex stream processing, especially that require kind of multi-stage pipelines that, there needs to be shuffling or something like that in between. Pulsar functions is lightweight processing, single stage, and so on and so forth. So some of for some of our complex analytics, like it only makes sense to use Flink in those instances. But definitely, we have thought about using, Pulsar functions for some of the more simple and lightweight use cases as well. And perhaps we will share more about that in the future.
Okay, great. I'm not sure if this one was answered. Are there any advantages of using Splunk versus Splunk Connect for Kubernetes to collect the logs from Kubernetes clusters?
I'm not too familiar with Splunk Connect, so I'm afraid I can't really answer that question.
All right, that is okay. Maybe there's some resources. If
Yeah.
you want to visit the Splunk website, I know there's a little chat bot that should be able to direct you.
Mm-hmm.
We have another one. This is from Tom. It says, what time, I think what kind of answered. Okay. What type of workloads are better for Flink rather than Presto?
Okay, that's an interesting kind of orthogonal question to our talk, but sure, I can answer that. So Flink is for more for definitely Flink it has the strong capabilities of real-time processing, right, on streams of data. What Presto is really querying data that's already somewhere, that's already stored somewhere, in a more kind of a batch in a periodic fashion. So that's kind of the difference there. That, for example, a lot of what people use, Presto to do is, query data that's already like, in a S3 basically bucket or something like that. While Flink is definitely basically processing and able to query the data that's basically in a streaming fashion. Sure, like there's also ways for Flink to query data kind of in a backfill manner of historical data as well. But that's kind of the difference here, that Flink is more oriented towards stream processing, while Presto is kind of definitely just for the batch style type of workloads.
Got it. Great. All right. Well, we want to thank you again, Jerry, for being the guest speaker at the Bay Area Pulsar meetup this month. We've had a number of questions come through of whether this recording will be made available. And yes, it's being recorded and we will be posting it. We'll send an email follow-up to all of our attendees, and we'll also be putting it up on YouTube. So with that, I want to thank everyone for joining and hope to see you at next month's Apache Pulsar Bay Area meetup. Thank you, guys.